Welcome to our class session where we'll be discussing analytics or business analytics, business intelligence, and data mining, as well as a little bit on dashboarding. As in a little bit of administrative items, please be aware of the due date for the database project, and for our next class, we'll talk about this a little bit more at the end of the video as well. Now, business intelligence and business analytics are a little bit hard to define. Let me kind of talk you through how we're going to evaluate them for this class, but be aware that the definitions for business intelligence and data analytics are still being decided in the industry. Sometimes things change over time, and this is one of those items. So here's from Gartner. You can see on the video that Gartner defines business intelligence as sort of an umbrella term that includes applications, infrastructure, tools, best practices to do analysis of information to improve decision making and performance. So essentially they're talking about a bunch of items, IT and otherwise, that allow people to take raw data and transform it into meaningful information. Similarly, if we were to look at a definition of business analytics, we would see that Gartner also has a very similar definition. Solutions used to build analysis models, simulations to create scenarios, understand realities, and predict future states. Business analytics includes data mining, predictive analytics, applied analytics, and statistics, and is delivered as an application suitable for a business user. So these terms, business analytics and business intelligence, seem to have very similar concepts. We use them to take raw data, apply statistical and other types of analyses, and produce meaningful information. So at the end of the day, what then is the difference? All right, well, in this class, here's how we're going to define things. We're going to talk about how business intelligence tends to focus on past performance. It includes all of these items, tools, systems, methods, processes, where we take data and look for meaningful information where we can make decisions, but with a focus on previous data. We look at the key performance indicators for what we did last quarter. We look at, what's the aggregate amount of sales that we had in the last 5 years to help us forecast for the future. And so we're really looking at previous data, not anything about what's going on in the future. Business analytics, on the other hand, tends to be much more future-focused. So in this class, that's going to be our major distinction. With business analytics, we're applying some of the same tools, but we're using them for doing, like I said, forecasting. We're building predictive models to help us try to predict the future, and we're looking at generating new insights. We'll talk more about that when we get to data mining. So that's the main difference here. Now, I do bring this up because these terms really do overlap a lot. Some people have very narrow definitions of business intelligence and of business analytics and are very strong in their opinion of these two topics. Others use them interchangeably. And so in this class, I want to be clear on how we're going to use them, but realize that the industry is changing and these terms may change over time. One thing that's interesting is let's pull up what Google has to say about these things. So this is a tool from Google called Google Trends that allows you to look at search terms over time by different search terms and compare them. And so if we were to look, there's some geographic information here, but if we were to look at this, you'll notice that business intelligence is the blue line here, right? And these are normed over time. These aren't raw data. These are normed based off of a baseline value. But you'll notice that over time, the term data mining, represented by the red line, has kind of dropped in relative to business intelligence, and that business analytics, the yellowish line at the bottom here, has just steadily increased and increased and increased. And in terms of the overall number of searches relative amongst these terms, you can see that they're almost very similar in terms of the number of terms, with data mining still the most popular search term, but we could also add in just the general term analytics, and we'd see, that is blowing up over time in terms of the search going on. And so, this is a very hot area, whereas, analytics and business analytics, and we could even search in predictive analytics and add those terms in. And all of these are getting more and more popular over time. And so you can see that this is a hot area. All right, so where do we get all of this data from that we're doing our business intelligence, we're doing our analytics on? Where do we get it from? Well, generally we get it from all of our other systems, some of the things that we've talked about. We get them from databases that are part of our enterprise systems, our ERPs, our customer relationship management system, our supply chain management system, as well as from other sources. Sometimes we get data from public information. A lot of people are doing things like sentiment analysis, looking at emotional communication using Twitter data or Facebook data or other things. We might get some of our data from that. But a lot of times we'll just get it from our own internal systems, and those get transformed into, we've talked about this already this semester, those get transformed into non-normalized data and put into a data warehouse so that we can perform this analytics. And then once we do our analytics, what's the output? Well, we might have graphs, we might have reports, we might have predictive models, we might have dashboards. We'll talk about some of these things as we go along. And in your project, your analytics project, you'll be focused mostly on doing data visualization, creating things like charts out of data. So where does this show up? Well, data science and analytics and business intelligence is kind of entering into every area. Okay, it's been very strong in customer relationship management for a while. We've used a lot of predictive models in financial, analysis, stock market predictions, and in marketing. But it's certainly getting into every aspect of management and of business. In supply chain management, we've used statistical analysis for a long time, but the types of statistical analysis that we're using have changed a little bit over time. HR is a huge area where technology and analytics are just booming in that area, and HR is dramatically changing in terms of how it looks and how it works as a field. We've talked about a little bit with marketing with price. Price is one of the most difficult decisions that companies come up with for many industries and many products, and help analytical support to help this is important. And then things that we'll talk about a little bit, because they're in the media all the time, is sports and political election analytics. And so these are a couple of areas that are very, very popular because people get excited about sports and about political elections. And so we'll use those as some examples as we go forward. All right, so why do we care about this? Well, as it turns out, the companies that tend to have strong business analytics or data science, whatever term we're using here, when they have skills in that area, this tends to lead to higher profitability, greater revenue, and overall return for the shareholder. Why, though? Well, the reason is because we use analytics to actually get information from our data. Okay, it enhances our understanding of our data because we turn it into information that we can use to make decisions. Okay, so it's the processing part that helps us to endow our data with meaning and purpose for decision making, so we can apply it as knowledge. So it's also considered to be a competitive advantage. Organizations who invested early in analytics and who are continuing to invest in analytics often are seeing a competitive advantage relative to their immediate competitors who are not yet or are lower on the scale of adopting these technologies. And we've already talked about this. One of the outputs is, business analytics allows us to create reports, graphs, visualizations, dashboards, etc., that allow us to make decisions quickly. And for managers who may not have statistical or analytical backgrounds to make good decisions. So this is an overall process map of what analytics looks like. And we could go into more depth on all of these things. So first, let's talk about data acquisition. How do we get our data from various sources into a form and into a location where we can perform data analytics or business intelligence analysis on it? Second, we look at data analysis. All right, what is the actual statistical and other analyses that we're going to be performing? And then finally, what are we producing as an output for our data and analysis? I mean, for some people, it might be just fine to run the statistical model and spit out the results of our regressions or our ANOVAs or whatever statistical models we're running. But that isn't often the best for users who are less statistically savvy. And so we need to produce some of the things we've talked about, reports, dashboards, decision support systems we'll get to in a little bit, predictive models, forecasts, etc. Now, if we were to have a business intelligence or business analytics program here, and many undergraduate business schools have added a business analytics major or concentration in the last few years, we'd probably spend a whole class or even two just on this first little extract, transform, and load section, okay, the ETL process. ETL is really a important and to some extent painful process. In our company, what if we do business in multiple countries? You would think that it might be pretty easy to just throw all of our sales from one country into our data warehouse and our sales from another country into a data warehouse. The problem is, which currency do we use? Do we just keep the raw currency that each country sells in? Do we just say, oh, okay, well, we need to convert from euros to dollars and we'll just do that once? Do we need to convert at the time that the currency transaction or the transaction took place in the exchange rate at that particular time and location? Well, probably, okay, and all of those things become problematic. What happens if we have missing data? How do we handle that? What if our data has inaccuracies? What happens if we have different product IDs for one market than we do for another market? Well, we need to map those up if we're going to get realistic data out of it. And so extracting from multiple different systems, from different countries, different divisions, different subsidiaries, so that we can actually do useful and meaningful data is very challenging. Then, cleaning up that data, fixing the problems. This data acquisition part is very important. It has to do with the garbage in, garbage out information accuracy we talked about earlier in the semester. It's very important. We're going to talk next about data mining in a little tiny bit of depth, but there are many different types of analyses that we can do. We can do online analytical processing, we can do multidimensional analysis, some things that you covered in DS 101 and other classes, but also other analytical techniques. Let's do data mining. Data mining is fun. So data mining, if you remember from your DS 101 classes, for those of you who have taken that, or any other statistical classes you might have taken, one of the kind of the rules of doing statistical analysis is that we shouldn't do what we in the analytics world tend to call a fishing expedition. We shouldn't go fishing through our data, and by what I mean by that is we shouldn't just go into the data without thinking beforehand what we want to analyze and just look for things that are correlated and then say, oh, okay, life is good, right? We should come up with a hypothesis first, and we should test that hypothesis. We shouldn't just go randomly looking through the data. Well, data mining basically says, you know what, we're going to ignore that rule. We're just going to go mathematically through our data and try to find patterns that we didn't even realize existed before. Here's an example of that. Now, this one happens to be an inaccurate example. It's not true, but it's widely spread around. And so let me give you an example. It's something that could theoretically exist, even if it didn't exist. There's a rumor that at Walmart, between the hours of 9 p.m. and 6 a.m., that there is a high correlation between sales of diapers and sales of beer. Now, why might that be? Well, you can come up with a plausible story of, some terribly tired parent out of diapers and in an emergency needs to come in, grab diapers, and on their way out also grab beer. To the point that it was rumored that Walmart had come and placed next to the beer a little bit of diapers, and next to the diapers a little bit of beer. Now, none of that's actually true. but it's the kind of pattern that could theoretically emerge in our data. Now let's look at a couple of examples. So first, Amazon. Amazon constantly goes through their data and tells people what exactly are the best sellers. You look for a product on Amazon and it will give you recommended products. And we can look through in any department. Here are in toys and games, the best-selling product. Wow, it looks like something finally unseated, Cards Against Humanity. Cards Against Humanity had been the number one selling item on Amazon in the toys and games section for years and years. And so we can look in any of these, we can look in movies and see what are the top selling movies. And there we go. Trolls with Justin Timberlake. Awesome. Suicide Squad with Will Smith. More Trolls. Okay. And we can go and look at various different items that are being sold on Amazon. So that's an example of doing some analytics of their own sales data in order to identify which are the top sellers. Now, if we go back, we can also look, here's another couple of examples from Amazon. All right, so let's check out this product on Amazon. We've got some, no relation to me, Wells Lamont work gloves. We've got some nice little blue work gloves here. And let's say you needed some gloves, right? You might say, okay, well, what are the products that are recommended to sell with these gloves? Because sometimes that's useful to look at the frequently bought together. And we'll go down here and we'll scroll down and say, oh, okay, well, looks like some people who bought this glove also bought this other more darkly colored glove. Okay, great. But we can also look and say, okay, well, looks like some people bought these nice little chemical protection coveralls, and that makes a lot of sense to us, and that people bought some gas masks. But you might also wonder, well, why in the world were people who bought these gloves also buying blue raspberry rock candy? And if we continue going through here, we might see that, oh, they also bought some glasses and a nice little hat. And for those of you who are fans of the show Breaking Bad, you would understand exactly why this is, because these blue gloves might have been useful in purchasing for a Halloween costume to be Heisenberg. But for the rest of the people, you look at this and go, well, I don't really understand, because why would anyone buy blue raspberry rock candy when they're buying industrial gloves? Okay, well, it's because Amazon has mined their data to try to find items that are frequently purchased together. Well, the last link that was put in the slides is now out of date, unfortunately. Amazon's constantly updating their product recommendations based off of internal data mining. But for a little while there, various red sweaters on Amazon were very popularly bought with certain types of glasses and white ties because of Mr. Ken Bone, who was kind of the celebrity star of one of the presidential elections during the last election cycle. And so those product recommendations, unfortunately, aren't there anymore, but were there when I created the slides. Let's talk about another, though, example. So this is a real example. One thing that's very interesting is Walmart figured out that when they were doing some data mining, they were looking at weather-related data. So they were incorporating weather data with some of their transactional data and trying to figure out what products might sell better or worse in certain types of weather. And what they found out is that whenever there is a hurricane, okay, or a hurricane's threatening the Gulf Coast of the United States, strawberry Pop-Tarts are the first things to go, first things off the shelf. Right? Now, this would make sense a little bit, right? Because they're convenient to eat, they don't require heat, they can be eaten with water, they have a fair amount of calories, so people who are in an emergency situation can eat these. But it's strawberry Pop-Tarts. The others don't sell quite as well. They eventually sell. If you've ever been in an area where there's an emergency, they eventually sell. The stores often sell out of products, but it's strawberry Pop-Tarts. So what does Walmart now do when there is a hurricane threatening? They make sure with Kellogg's that there are plenty of strawberry Pop-Tarts headed towards the Gulf Coast. All right, so the next examples, I've got two examples going on, and I've got these two videos. One of them talks about Target, and one of them happens to talk about Moneyball. Because of copyright issues, I'm not going to embed them in the video, but I'll put them in as links next to the video that you're watching right now. So go ahead and check out the videos. First, the video on Target, and also the video about Moneyball, about sports analytics. All right, so hopefully those were very interesting videos. The Target video is a great example of how we can use some data mining in order to look at patterns and develop our models for whether someone, in this case, was expecting a child or not. And then the Moneyball example is a really interesting one. It's kind of a popular movie, but it was kind of strange because baseball has always cared very much about data and about statistical analysis of the data, except for nobody until the Oakland Athletics during that year had ever really meaningfully correlated any of those statistical analyses, or the statistics that were always calculated, earned run average and batting average and on-base percentage and all of those statistics that get reported by the radio broadcasters and TV broadcasters. They hadn't really correlated those with winning games. And so sports analytics kind of was born out of that. Nowadays, it is very, very rare for a NCAA Division I football or basketball team not to have a full or part-time statistician. And the big programs have many of them. NFL teams have small armies of statisticians trying to figure out what are the best lineups, what are the best players, what are the best ways that we can use certain recruiting data to identify the best players, especially ones they're kind of the under the radar players that nobody else is going to catch up on. And so sports analytics has become a huge area. There's a very famous MIT conference every year on sports analytics, and it's becoming very, very important. Here's a very simple example from a few years ago. Should a football coach go for it on fourth down? If you're not familiar with football, you have each team has 4 attempts to move the ball 10 yards. Usually, though, if they are not able to move the ball 10 yards in 3 tries, they will either punt the ball, kick it away to the other team way down the field, and so the other team has further to go, or they have the option of trying it again on the 4th try, on fourth down. But if they don't make it, then the opposing team gets the ball right then and then can go the other direction. And so should you go for it on fourth down? Well, as it turns out, if you do the statistical analysis on it, it depends, of course, on how many yards you have left to go and a number of different factors. But as part of analysis like this, people realized that coaches were being too risk averse. Because what happens if you go for it on fourth down and you make it? Right? Everybody likes that. Okay, it's good. What happens if you go for it and it's unsuccessful? Well, if you're a professional coach or even a college coach, you might get hammered by your fans and by the media, and you might look bad. But in terms of winning the game, coaches should have gone for it more commonly, according to the statistical analysis. And so, as a result, in recent years, people have gone for it on fourth down a little bit more frequently than ever before. There's a similar thing now in the NFL with 2-point conversions. As the field goal, or not the field goal, the extra point line has been moved back, it actually makes more sense to go for it for 2-point conversions. And many teams have done that and actually done it unsuccessfully and have been kind of hammered for it. But in the media, well, let's kind of watch. The analysis is kind of affecting the game and how it works. Another area that has become really popular in the last little bit as a way of applying data analytics and data mining, predictive analytics, is in elections, political elections, particularly in this country, but also worldwide. And so these pictures are somewhat humorous, but some of the most popular and influential of the statisticians that do analysis of presidential and other gubernatorial and Senate and House elections. So on the left is a gentleman named Nate Silver. He created a blog called 538 several years ago and became really famous the last 2 or 3 election cycles for predicting all but one of the races, including the presidential races, the states in the presidential races, and as well as the different House and Senate races. He predicted all but one of them correctly. And then on the right is Sam Wang, who's a professor at Princeton University, also runs elections.princeton.edu. And they do presidential elections. And these guys are very famous. Nate Silver, his blog was bought out by licensed by the New York Times during the last election cycle 4 years ago. And people estimated that he was driving somewhere between 30 and 40% of the traffic to the New York Times just because of his website on doing analytics on politics. Because of that, ESPN and ABC actually bought out his site away from New York Times, and so a lot of the analytics stuff that you see nowadays, he runs it semi-independently, but a lot of things he does now is sports related for ESPN. But it's interesting that in this last election cycle, Sam Wang, the guy on the right, who's now eating the bug, he ate the bug because he predicted with over 99% confidence that Hillary Clinton was going to win the election, and Nate Silver, he had her chances at about 70%. And so, why I bring this up is, these aren't perfect processes. Okay, the data for all of their statistical analysis might have been flawed. The techniques that they used might have been slightly flawed. They might have correlated things they shouldn't have correlated, and vice versa. And so we have to be careful when we're making these predictions that they don't always predict the future exactly as we expect. And Professor Wang ends up eating a bug on CNN because of this loss, as he promised to do. And so anyway, this is an interesting area, something to follow, something to look at, but it's also kind of a cautionary tale that we're not always right with our statistical and our advanced analytics. All right, let's have a conversation about different analytical techniques. Now, I know many of you have taken DS 101, some of you have not. I'm not going to go into super much detail on a lot of the specifics of the analytical techniques, but I want to give you a high-level idea of analytics, what's out there, what's possible, and hopefully this section will be helpful as you move forward and looking into analytics, and especially those of you who might be considering data analytics as your career. So here's one way to categorize different analytical processes and techniques. So one type of analytics is descriptive. And this one mostly is associated with things like business intelligence. What has occurred? What's happening right now? Let's describe, what were our sales this quarter? What was our sales yesterday? What is currently occurring? Predictive analytics is more on the analytics side, and this is what's going to happen in the future, where we try to forecast and guess and predict. And prescriptive analytics, sometimes we talk about this term in terms of what should be happening. Okay, we're predicting that something's happening, but maybe what should happen. And this also is related to issues like policy and, whereas, in some cases we have some outcomes that we know we would like, and how do we change things to get there? It also relates to optimization when we're trying to meet some optimal goal of efficiency or something like that. All right, so here's some examples of that. So on the top, hopefully this is visible, the red text here. At the top we have more predictive and prescriptive analytics, and at the bottom we have descriptive. So in the bottom we have things like alerts, queries, reports, standard reports. These are just kind of things that, what is currently happening, how often are we getting that information, and things like that. Whereas at the top we have optimization, what is the best possible thing that could happen in this situation in terms of, like I said, efficiency or other metrics? What will happen? What happens if we try this next? And why is this particular item happening? Okay, those are kind of the types of questions that we can answer with the different techniques. Now, as a reminder, let's talk briefly about, back from the database section, let's talk about star schemas, and I also want to talk about cubes. So if you remember a star schema, this is the type of data structure that data warehouses tend to use. We take our data out of its normalized tables, like we did with the database project, and we reorganize them so that we have a single fact table, all right? And then we have various dimensions about that particular fact, various different dimension tables. And so the fact table is usually about something that we care the most about, like maybe a transaction or a sale, whereas the dimension table gives us more information and details about that sale. All right, so for example, in this picture, we have the sale table is our most important, our fact table. And then the product, customer, and store tables here, these are our dimension tables. And they were linked together, okay? But the dimension tables are helping us to get information about the sales in more detail. All right, so this is how we organize things. Here's an example of how that might work if we were to put, there's a little bit of sample data in here where we've got our various different sales, and those are related to our products. Again, we have primary keys and foreign keys here, but in the middle we have our sales fact table and then the various different dimension tables in order to give more information. Now, cubes. Cubes are another way that we organize our data in order to do certain types of analysis. So a cube is a dimensional table. Now this could be a two-dimensional table. It'd be much like a Excel spreadsheet or a traditional database table, but it can also be more three or more dimensional, higher dimensional objects. And so the idea with cubes is that they allow us to create these two-dimensional views by slicing the cube up. Here's an example of what I mean by that. So let's say we have a cube. This one happens to be a three-dimensional, a true cube, but we've got a variety of products. We've got some different months for these particular sales. And we have some measures. In this example, the measures are how many units, what we sold, how much revenue did we garner from those sales, and what are our costs. And so there's these three different dimensions: products, months, and measures. And if we wanted to drill down a little bit and only analyze, for example, one product category, the blue shaded category right here, we could take a slice out of this three-dimensional table and only look at the shoe sales along the measures of units, revenue, and cost across a number of different months. And that's what the table on the right represents, this slice out of our multi-dimensional cube. All right, now for some of you this will be a refresher, for some of you this will be new, but I want to go through some very basic, not how to do things, but what analytical techniques are even available out there. What are the kind of the basic things, and what are the kind of cool things that might be out there if you really are interested in this topic. So, first of all, we have to distinguish between what's a population and what's a sample. So a population is all of the things that we're trying to study. Okay, maybe it is all of the people that could potentially buy our product, or maybe it's all of our employees, or maybe it's everyone in a particular sports league, or everyone who's ever played in a particular sports league. What are the entire population? Now, usually it's really difficult to examine the entire population of whatever it is we're trying to study. So instead, what we do is we sample, hopefully randomly, from the population, and then based off of those samples, maybe we do, for example, in elections, they go and they call certain people or ask certain questions of various people and try to get at what the whole population is going to vote like, even though they're only asking a few people. And so we then use statistical analysis to, based on those samples, try to figure out what's going on with the population. So here's some things that we can look at. So here's some measures of what we call central tendency. This is some things you've calculated before, some of you. Things like the mean or the average. Okay, so this top graph right here, you can see that this is the average value of 5.843 in this sample that was taken. So our maximum value is close to 8, our minimum is 4.3 or somewhere in there, but our mean, our average, is somewhere right here in the middle. Okay, so that's one measure of central tendency, but it can be skewed. Another measure of central tendency is the median. All right, so what is the middle number in here? We can also get information on the mode, what's the most commonly occurring one in a series of numbers. And so these all give us an indication of what are the sort of the most important or central values in a particular distribution. All right, we also have measures of dispersion, or how spread out the data is. Okay, so here's some examples of, the median gives us kind of the middle data, and the mean gives us the average data. But how spread out are things? What are the minimums and the maximums? What are the ranges? What are the upper and lower quartiles? Meaning, if we were to divide our data into quarters, where do those quarters lie? Are they close together, or are they far apart? We also can evaluate based off of, do our data follow a expected distribution of data? For example, we have some very standardized distributions. One of them we call the normal distribution, based off of what would happen if we sample from a particular population. And so your standard distributions have a nice little peak in the middle where it's more common to have an average amount, and it's less common to have an extraordinary, either really high or really low values. And so here's some examples of distributions. When we start to bring this up into multiple dimensions, and you don't need to know any of those math equations at all, but when we start to bring into multiple dimensions, like we did with our cubes, when we have multiple dimensions, multiple measures, then we need to start thinking about a distribution that isn't just a two-dimensional normal distribution, but realistically a 3 and 4 and 5 and multiple dimension distribution. And so when we evaluate multivariate distributions, we're evaluating something that looks, for example, this is a three-dimensional one, but it could be higher order as well. Now, when we test a hypothesis, we have a guess. We make a guess. Hey, is our particular sample, is it the exact same as what we would expect from a random sample, or is it different? Would we reject that? And so here, for example, we have the values of, the blue line. I'm going to draw this with red, but the blue line here represents the normal distribution. And if we're in that range, we're not going to reject our null hypothesis that nothing is the same or nothing is different. But if our distribution ends up being, over here, the actual original red, then we would reject that hypothesis. Now, at some point in the middle here, though, we have to make a determination onto where does the boundary conditions lie. Okay, we can have errors, for example. We can have errors that are called type 1 errors. These are false positives, where here's the nice example of that, where this gentleman is told that he's pregnant, even though he is not pregnant. So that's a type 1 error, and sometimes we have those errors. And then we also have type 2 errors, where this woman who actually is pregnant is told that she is not. And we have to deal with those types of errors, and which ones are more problematic, which ones are less problematic. And so we have to try to decide that and based our statistical analysis off of that. Let's keep going. Correlation is a very important characteristic. Correlation is the idea that if you have one variable and make a change to that variable, then some other variable also has a change. They correspond with each other or correlate with each other. And correlation, the statistic correlation, ranges from -1, perfectly correlated but in the opposite direction, to +1, perfectly correlated in a positive direction, and a 0 value for correlation means that these variables are not at all correlated. And so you can see here in our example, these are perfectly correlated data. We've got data that, a change in one variable, the x dimension, perfectly changes the y dimension, and it's always exactly the same. This is a linear change, and so it's a perfect correlation. On the right-hand side, we have, sort of the opposite, whereas you increase one variable, it decreases the other. It's a perfect correlation between those two. In the middle here, look at this dispersion of values. If you were to plot a trend line through these, you'd probably plot one that is pretty flat, okay? That there's really no correlation between those. There's no, you change one variable, it doesn't really correspond to a change in other things. And then we have values in the middle, whereas, for example, this one right here, which has a 0.8 correlation, you can see that, generally speaking, if you increase one thing, it tends to increase the other variable. But there's some variation there. It's not a perfect correlation. So that's one of the things that we're looking at in terms of statistics, is how things correlate. Now we have to be careful, because some data, for example right here in the middle at the bottom, some of these shapes right here, like this one right here, clearly there is a relationship between these variables. Clearly something is going on here, that there is a curvilinear relationship. It looks like a parabola here. But statistically, the correlation would be 0 if we're doing looking for a linear correlation. And so we've got to be careful. These values down here at the bottom here, clearly there is more going on. This one's a sinusoidal sort of relationship, and there's other things going on here that other statistical techniques might be able to evaluate. All right. Many of you have performed, whether it's in high school, whether it's in DS 101, but many of you have performed what's called a linear regression. The idea with a linear regression is we take our data, we go and we try to fit a trend line to that data, which is minimizing the distance between each of these points overall, and then we end up with an equation where we can hopefully predict a value. For example, if a new sample was taken and we had a value of 40 for that particular data point, we would expect that the value on this other dimension, on the y dimension, would be about, 11 or so. We would expect it to fall somewhere in here. And so if our value fell right here, for example, we would not be surprised. It falls within a general range, and that helps us to predict what goes on. Now, sometimes, though, we don't use data that fits our normal regression or our normal distributions. Sometimes we do things, we use models, for example, like when we have a categorical variable, a yes or a no, or a 1 or a 0, it's not really appropriate to use certain types of distributions, like a normal distribution, as we might use a logit distribution or a probit distribution when we're dealing with things like categorical variables. Now, as we move towards more multivariate analysis, then our distributions tend to look a little crazier, depending on which type of things we're trying to fit. And so just be aware that as you move to multidimensional, multivariate statistics, things get a little bit more complicated. Another thing that I wanted to point out is there's a statistical technique that's becoming more and more common called structural equation modeling. And it's based off of ideas from simple regressions, but it is the idea that we can take multiple different items, like these items on the left, and we can map them to a concept. In this case, we're dealing with a healthcare concept. In fact, a lot of my examples, I'm dealing with healthcare concept because I've been doing some training on healthcare analytics. But for example, a shared identity might have a couple of different items that are related to that. And a physician's behavior might have a couple of questionnaire items or some things that can be measured about a physician's behavior, like whether they smile or whether they listen. And all of these items might help explain why a physician's behavior leads to trust in a physician. And we can evaluate that trust in the physician by a number of different other dimensions. And so the structural equation modeling is kind of, to some extent, like regression on steroids, where we do lots of regressions to help us understand an overall big picture model. All right. So here's an example. What kind of tests do I perform? And I don't expect anyone in MIS 101 to know this slide, but just for your information going forward, this is not going to be on the test. But how do I test whether there is a difference between different groups? Well, you can perform a test called a chi-squared test. That's one way to do it. You can perform a variety of different types of t-tests. You might have covered that in DS 101. You can perform different types of ANOVAs and ANCOVAs, which are looking at the analysis of variance and the analysis of covariance. These are looking at differences between means, and we can also do the multivariate versions of those tests. Okay, well, how do we calculate and evaluate relationships between different variables? Well, we can do things like correlational analysis. We talked about that briefly, and regression. We talked about that. We can also do structural equation modeling and path analysis. How do we evaluate membership in a group? Well, we can do logistic or probit regression to determine whether someone is or is not in a group. We'll talk about more advanced methods of doing that in a little bit. How do we reduce our data? Okay, what happens if we've got a ton of different factors or components? How do we reduce that for certain types of analysis? Well, we can do something called principal components analysis or factor analysis. And also, what happens if our data is hierarchically related? That can cause problems statistically. What happens if we're dealing with groups inside of companies, inside of industries, so the data is related hierarchically with each other? Well, then we have to do different types of modeling based off of regression, but hierarchical linear modeling, or certain types of structural equation modeling. Again, this slide is a little more than I want to get into this class, but I want to make you aware that these sort of things exist. All right, let's get into some of the advanced metrics, the advanced analytics, and I want to talk just mostly conceptual about these items. So how do we even start to handle big data? We talked about big data in our database class. How do we even think about handling it? Well, one of the ways we deal with this is something called MapReduce. So Google and a group at Yahoo and other ways have started coming up with this concept of MapReduce, where we take some data, we run it through some processing and shuffling and reduce it so that we can do better statistical analysis on it. Now, this is a highly simplified sort of description of MapReduce, but MapReduce is a very clever process, and it's been implemented into a number of different products. But in particular, one of the most common products is called Hadoop. And a lot of our big data analytics, or even analytics on smaller data, tends to use Hadoop. Hadoop is an open source project that's run out of the Apache Foundation for doing this algorithm, this MapReduce algorithm, so that it can be used, the data can be used in big data analytics. So how do we even start with big data analytics? All right. Well, the proverb of eating an elephant one bite at a time really does apply here. So how do we handle this big data, which is really challenging in some ways to deal with? Well, oftentimes we start with very simple statistics. We start with things like means and median, and look at ranges, and that can often be very revealing in helping us deal with more advanced techniques as we go. Now, we've talked about data mining already. I also want to talk about this idea of machine learning. Machine learning is the concept that we have algorithms that allow our computers to do a little bit of learning. There's a couple different types of categories of machine learning. One of them is supervised, and the other is unsupervised learning. Okay, so here's what we mean by that. Supervised learning is where we add in parameters and kind of watch the process. There's human intervention, and unsupervised learning is when the algorithms are just allowed to run. Let me be more specific on that. So here's a couple of techniques. With clustering or cluster analysis, what we do is we throw a bunch of data and some measures into this clustering algorithm. And the algorithm tries to identify data points or subsets of the data that are mathematically close to each other. And there's a number of different ways of looking at mathematical closeness. But this is to help us identify patterns or various structures in our data. This is an unsupervised learning algorithm that we make no prescriptions as to which group. We don't have an independent variable. Like the green group is one particular type of company and the red group is another type of company. We don't add any correct answer or right answer in there. The algorithm helps to identify the clusters. Now, classification is different. With classification, we identify the groups beforehand, and we use the calculations, the mathematics, the statistics, in order to identify rules that help us to divide up these groups. This is supervised learning because we're giving the answer, which are the groups, which group membership each data point is in, and then helping to identify the rules that we could, in the future, classify a new data point into those groups. So here's an example. What if you wanted to determine whether someone has diabetes or not? Okay, so this is a medical application. There's some very clear tests. Okay, so if you've got certain sugar in the blood values that above certain percentage, then that's clearly the person has diabetes. But there's other things that help to cluster people, things like their blood pressure and whether they receive the flu shot, and certain foot exams, and certain fat levels and cholesterol levels, whether they've taken aspirin or not. All of these factors can be used to create a rule on whether it's most likely on someone has diabetes or not. And so this is an example of creating these this classification algorithms, these rules to help us identify whether someone fits into a certain category or not. Here's another thing that's interesting. We've talked about this a little bit with Amazon recommendations. With association rule learning, we help to associate different things that are often clustered together. So for example, let's say that we have these three carts. We have someone who bought milk, bread, and cereal, someone who bought milk, bread, sugar, and eggs, someone who bought milk, bread, and butter. How would we know which items are commonly purchased together? Are sugar and eggs commonly purchased together? Well, maybe. Or maybe it's milk and bread. Oh, it's actually, if we look at this basket, milk and bread, milk and bread, milk and bread, oh, those are commonly bought together. And so we can use association rule learning and the advanced techniques in that type of algorithm in order to evaluate this. We can also do various, this is more common in supply chain and other analytics, but we can look for outliers. So here's an example of looking for a fraudulent behavior. So we might have, for certain types of data, the chart on the left is normal, the chart on the right is fraudulent, and we can use various different types of algorithms, Benford's law and others, to try to look at anomalies. We can also do something called sequential pattern mining or collaborative filtering to help determine, for example, if you are similar to someone else. So maybe, have you ever tried to go and, maybe you are interested in a product and you go and look and see, hey, I'm pretty similar. I like similar things to my friend. Maybe I'll ask them what I should get. For example, this gentleman on the right is someone who likes similar things to the gentleman on the left. They both like pizza. They both like these type of, looks like chef salads. The guy on the right likes this particular type of soda, and maybe the company, if they knew all of that information, maybe they would recommend that to the customer on the left. And so you can use what we call collaborative filtering to help predict what someone would like, or at least describe it as well. Another type of analytical technique this is an advanced technique, is something called neural networks. The idea with neural networks, they sound really fancy, and in some extent I guess they are, but the idea behind them is that the way that scientists have determined the brain works is actually having these different neurons that are related together and have relationships amongst each other. And the way that the neurons in your brain work is, certain over time, certain weights are given to certain things to help make decisions and to do processing in the brain. And so neural networks is a way of predictive by having a number of different inputs, a determined amount of what we call hidden nodes, and there can be multiple stages or layers of these hidden nodes to help determine output decisions. This is useful for certain types of decision-making behavior as part of a lot of machine learning algorithms. Social network analysis is really interesting, and this doesn't have to be necessarily social networks like Facebook and Instagram and Twitter, for example. But this can also be, this example is for healthcare provider networks, and so how do these networks relate to each other? And that can be very fascinating and help us to identify who are the gatekeepers in particular networks. For example, who are the most important people, not by job title, but by the connections and by the relationships with one another. There's a number of techniques for handling social networks. This next one is text mining. So I've used text mining in some of my research. Text mining is the idea that we take text and we run statistical algorithms on them. It can be supervised or unsupervised in order to evaluate certain things. One of the most common things is sentiment, whether something is emotional or not, but it could be a number of different things that are trying to look at in sentiment or in text mining. And then this last piece is doing something called data stream mining. So what's interesting is that most of the statistical techniques that we talk about and that we use, we gather our data, we put them into the data warehouse, and then we analyze them. And so the time that those transactions and those things occurred may have been months or even years in the past, certainly days in the past in most cases. But what happens if we're trying to get data real time? If we're trying to get real time, for example, Twitter data, or what happens if we have a lot of Internet of Things devices? You've got your smart watches and your smart fridges and your smart this and that. What if we're trying to gather data in real time from those devices and then analyze it and provide a dashboard? What sort of techniques can we use? Well, there's actually a very nice and new way of doing these sort of stream data mining, where we do this type of analysis in real time. Again, the details of all of these analytical techniques are kind of beyond the scope of this course, but I want to give you at least an idea of what's available and what's out there. All right, so now that's data mining. Let's now talk about decision support systems. So this is an area that is important. We recently did, this is a side note, we recently as a college did a sort of a big exam, the major field exams, and it's an exam that is given to hundreds of business graduate student or business undergraduate students every year, and so we were kind of competing against them. And one of the areas that we did really well on was actually MIS curriculum, except for one question. There was one question about decision support systems that we didn't do very well in as a college. And so I want to make sure we're clear on this because this is important. There's a category of information systems that are called decision support systems. And the idea is that they help people to, well, simply make decisions, right? That we have problems that managers and others need to make decisions on them. And we have software that helps with that. Now, these decisions and the decision support systems behind them depend very much on the nature of the problems. So for some of the problems that we have, structured decisions, these are problems that are very routine, that the parameters of the decision are very well known, and that there are some fairly standardized solutions. Well, if the solution is very standardized and the inputs to that solution, the parameters, are very routine and repetitive, this is something that a decision support system can actually almost take over or even fully take over and automate this decision. Should we, sell or buy with certain conditions? Well, in some cases, we would always want to buy. And so we make those repetitive decisions, automate them. For example, in the stock market, there are many, many decisions that are automated, both structured decisions and semi-structured decisions. Semi-structured are ones where we don't really know all of what's going on. Things aren't as routine and repetitive. Sometimes they take human intervention, and sometimes there's judgment that needs to be performed there. But a lot of the things can be automated and are routine. Okay. And then the last category are these unstructured decisions. These are sometimes called fuzzy or complex problems, and these are ones which there's not really any standardized solution. These require individual judgment. These are things like, what should be our corporate strategy? It's very hard for a computer to decide that for the company. But implementing certain aspects of the strategy, well, that might be something that the decision support system can help with. We've talked about this already a little bit with decision support systems, but these use a variety of different statistical modeling or models, analytical models, rules, business analytics, and as we just talked about, the more unstructured the problem, sometimes the greater the need for a decision support system. So a decision support system may not be able to make decisions for unstructured problems, but they can certainly help out and provide potential solutions. For example, consider if you're a physician, you're a doctor. What if you need to decide what your patient should be prescribed with? Okay, here's the particular, the symptoms that the patient has. Here's their history. Here's their current drugs. What should they prescribe? Well, as it turns out, some of these things are very routine. Okay, if you have this particular condition, well, you give this particular drug. But other things become less routine. Okay, what happens if this whole suite of symptoms show up? And what happens if that particular patient also has other conditions or other drugs that they're taking that might interact with certain drugs? Well, the doctor still needs to use their judgment, but oftentimes the systems, and many of them have medical decision support systems that help them to identify, well, this is probably the recommended drug or set of drugs to offer in this location or in this situation, but the doctor ultimately has the ability to prescribe what he or she feels is right to do. Now, we also have these decision support systems that include something called dashboards. So dashboards are a way that we can view the information very quickly. So based off of the analytical models that are run, we have graphs and other visualizations that help us to look at a glance and say, okay, things are going well. Oh, they're not going well in this area. And if we'd like, we can go and drill down, meaning get more information about certain aspects. So let's look at a dashboard. This is not a very pretty dashboard, but at least shows the point that I'm trying to get across. So here's a dashboard. In the upper left-hand corner, we have some of our key metrics. In this organization, customer satisfaction is a key metric, staff turnover is a key metric, order cancellations, and the sales year-to-date versus what our target is. These are our key metrics that we really want to keep close eye on. There's other things, our sales forecasts we care very much about, maybe revenue by country in the bottom left. And then here are some of the risks. We have a bunch of different risks and categories on the bottom right. So this allows a manager, this dashboard allows a manager to look at a glance and say, how are our sales doing? Oh, look at that. We are well into our to the green on this. In fact, it's very common for these dashboards to have the kind of the stoplight coloring, the red, yellow, and green coloring to help identify quickly whether things are good, bad, or somewhere in the middle. And we can see that, hey, our sales are good, but the pipeline might be weak, okay? And that helps to identify where we need to go. And maybe we look and say, okay, well, where's our customer satisfaction? Well, at the moment, it's not very good, and maybe that's contributing to our weak pipeline. Maybe our customers were buying stuff, but now they're not satisfied, and then our future sales are looking a little bit dicey, a little uncertain. And maybe part of that is due to our staff turnover. Our turnover is a little higher, in fact, quite a bit higher than we would like it to be. So maybe that's something we need to look at. And a manager could go and click on some of these aspects and drill down and get some more information about them. So dashboards are really, really helpful in identifying, at a glance, some of the key performance indicators and some of the, other, metrics, at a glance to help make decisions. All right, so what I want you to do next is, as a review, we've covered business intelligence, we've covered data analytics or business analytics, we've covered data mining, and we've covered dashboards. So I want you to fire up your top hat if you're doing this on the day that it's due. If not, you can do that. Come back and do that later. See as a review if you can answer the questions on top hat and identify which of the question items is associated with which of those concepts. All right, so the next slide, I placed a Dilbert comic, and because of copyright issues, I don't want to include that in the video. I'll include a link to it. But the video talks about one of the Dilbert characters, the pointy hair boss, is talking to Dogbert, and they're talking about the importance of dashboards. And so, this idea of dashboards and business analytics even creeps into our cartoons. All right, so that's the end of this video. I want to talk briefly about what's going on next. Okay, so we have now reached our spring break, or officially spring recess, according to Sac State. There will be no classes. Make sure to check the schedule on when that is, but there are no official classes and campus is not open. The next class that we will have will also be an online class. It has to do with business processes and systems development, and we're to do Top Hat Readings R11. Make sure to do the homework questions as normal prior to the start of class, and then also be aware of your database project due date. I'll be in my office hours. I'll be in my office during office hours, but please make sure to complete the project. And if you have questions, post questions on Slack. All right? Thanks.